We now look at the second type of improper integral when we have a infinite discontinuity at a certain point. So the function is not bounded over the interval we are integrating. Let's look at another important example over here. So look at the function f of x over, say, we have 1 over x to the power p, but it's on this interval 0 and 1. Okay, and we know that f of x going to infinity if p is greater than 0, right? That's what we have. So the function looks like this. If you look at the graph, it looks like this on this side. Okay, and this is 1. So we are trying to ask what's going to be the area under this curve over here, right? And that's the situation we have. So we define, just like the other kind, if we integrate from 0 to 1 and 1 over x to the power p dx, we use a limit. So we take the limit and t goes to 0. Okay, but of course t goes to 0 from the right hand side, and then we integrate from t to 1 and 1 over x to the power p and dx. So in a sense that we actually integrate only from t to 1 and then let t go to 0. Perfectly reasonable. And then we have limit t is approaching 0, and integrate this one. We have again the same antiderivative, so we have 1 over negative p plus 1 and x to the negative p plus 1. Okay, and then we plug in 1 and t. Okay, so that's what we have. Again, we have to say that p cannot be 1, otherwise we have 0 in the denominator. And then we have the following. This is equal to the following limit. T is approaching 0 here. When we plug in 1, we get 1. So we have 1 over 1 minus p. And when we plug in t, we have negative 1 over 1 minus p and t to the power 1 minus p. Now this limit, t is approaching 0, so we have to have 1 minus p bigger than 0, and then we have a limit. So this limit over here is equal to 1 over 1 minus p if p is less than 1. Isn't that interesting? We assume over here, of course, p is bigger than 0. Otherwise, we don't have an improper integral. What if p is equal to 1? Okay, you will see this equal to 1 case is always somehow on the borderline, and this is what we have. If p is equal to 1, then we have from 0 to 1, still x to the power negative p and dx, and we still have a limit. T is approaching 0 from right hand side, and from t to 1 and 1 over x dx, and we have log limit. T is approaching 0, and we have log x, plug in 1 and a t. So we will have limit over here, and t is approaching 0. Now we have log 1 minus log t. Of course, we know that when t is going to 0, log t going to negative infinity. So this one is positive infinity. That means it does not exist. Okay, and that's the important indefinite integral of 1 over x to the power p. Somehow we remember these results, that if p is less than 1, then it's going to be convergent. If p is greater than or equal to 1, it's going to be divergent. In fact, if we say sometimes we have something like this, 1 over root x dx, we may not realize it's an improper integral. In fact, it is. But this one over here, we can integrate just like the way we did it before. 1 over root x, if we integrate the antiderivative, it's going to be 2 root x and 1 and 0. And then we plug in, and that's going to be 2 root 1 and minus 2 times 0. And that's going to be simply 2 over here. But this is actually an improper integral if we pay attention to that. There is another catch about this type of improper integral. If we have an discontinuity in the interval, infinite type, within the interval, not on the not the upper limit and lower limit, we need to be very, very careful. For example, if we integrate from, say, -1 to 1, let's say we have 1 over x squared dx. This is actually a divergent improper integral, and this is not going to equal to, say, -1 over x and plug in 1 and -1. This is not going to be true. This over here, of course, you can get -1, -1 and minus 1 over -1, and somehow you get 0 over here. But that's not true, because we know that when we put 1 over there, actually we should get -2. We should get -2. The reason is there is a 0 in the interval. So 0 over here is inside -1 and 1. And 1 over x squared going to infinity as x going to 0. So we really have an improper integral. -1 over x squared dx is equal to -1 to 0, 1 over x squared dx, and plus from 0 to 1, and 1 over x squared dx. And both diverge. These two integrals, both they're divergent. They're divergent. So because these are improper integrals, they are divergent improper integrals. Okay, so be very careful if we have infinity value within the interval we are integrating a function.